All right, so today we're going to be calculating free energy using voltage, and we're also going to be looking at cells that are not under standard conditions and calculating their voltage. So the first equation, and this is going to be on your AP equation sheet, you don't need to memorize it, is delta G is equal to negative NFE. It's a correlation between free energy and voltage. So kind of makes sense. If you have a spontaneous reaction, what is the magnitude of the E, positive or negative? Positive. So if this is a positive, the negative here makes the delta G negative, so that's spontaneous for G as well, right? Okay, so what are each of these variables? The N is the common factor of electrons that you canceled out when you were balancing your redox. So if you had a 2 in 1/2 reaction and a 5 in the other, what would your N be? 10. So it's however many electrons you canceled out when you balance the equation, okay? S is a constant. It's called Faraday's constant. You've heard of a Faraday probably in physics, yes? But we look at ours a little bit differently. The number that we're looking at is 96,500. You don't need to memorize it. It's right here. It's also on that AP equation sheet. That is the charge that 1 mole of electrons carries, okay? So if you have a whole mole of electrons, the charge is 96,500. The units are joule per volt mole, and you can also do this in terms of coulombs per mole, and the units work out that way as well. But to make it work in this equation, we want the units broken down to joules per volt mole. And then E naught, we know how to get that, right? Right half reactions, go to the table, flip the oxidation, and add them up. And the unit on that is volts. So let's go ahead and practice this really quick. Start looking these up for me. Magnesium goes to magnesium plus 2 electrons, and then lead plus 2 electrons goes to lead. Let's do lead first. I always like to do the reduction ones first because we're taking them off the table exactly as they are. So does anyone find it? Lead 2 to 0 on the reduction potential table is negative 0.125. All right, and this is volts. And then the magnesium, okay, it's negative 2.356, correct, on the table? But because this is oxidation, we're going to flip it and make it positive 2.356 volts. Gosh, it's doing that wacky thing again. And we add these up. And when you're doing sig figs on addition, what do we round to? Lowest number of decimal places. So this is going to be 2.231. All right, now that we found the E, we're going to plug it into our delta G is equal to negative NFE and solve for delta G. Delta G is equal to negative, what is my N? 2, because that's just how many electrons moles of electrons we would have canceled out. Negative, no, that's 2 moles. F is 96,500 joules per volt mole. And then E, oh, look how convenient that worked. I almost planned that. Look at that. All right, that's awesome. So since it's a positive E, our delta G should come out negative. And when we solve, last period got, let's see, what did they get? Negative 431,000. And the unit on that, it's joules. But remember, even though these moles cancel, the AP on any delta G, delta H, or delta S wants you to report it per mole of reaction. Okay, so joules per mole. Don't convert to kilojoules unless you're told. Don't waste that time or the possibility of making a crazy mistake. So I'm only going to do one of those. I don't think that's hard. That's just knowing algebra and what to plug in. So you'll get to practice that in your homework and on some AP problems. Next up today is the Nernst equation. The Nernst equation is really, really important, and I would bet a lot of money it's going to be on the AP. Like I'm 99% sure you're going to have a Nernst equation problem. What the Nernst equation does, it converts E standard to a non-E standard. Okay, so if you have a cell that's not at standard temperature or something like that, you would use the Nernst. There are 2 versions. This is the version that we're most concerned with. I have yet to see this really on any APs in the last 15 years. What the first one is used for non-standard temperatures and concentrations. So if the temperature and or concentrations are non-standard, you could use this first one. But what's actually most often the case is they'll tell you that the concentrations aren't at standard. They leave everything else standard. So what was done to convert from this equation to this equation is just plugging in standard temperature for that T, putting in the R, 8.31, and then putting in Faraday's constant and combining that with that 2.303 and going from log to natural log, doing all that crazy stuff, you end up getting 0.059. Okay, so this is the one that I want you to be familiar with. I am not going to test you on the one on the left. I can tell you right now. So what are these variables? E cell is the E of the cell under non-standard. E naught is the standard potential. Where do we get that? From the table, flip the oxidation atom up. N is the same as it was in the last, your common factor of electrons. Now what about this Q? Our concentrations are not at standard conditions. So what they have you do is calculate the equilibrium. It's not K though. Can anyone tell me why it wouldn't be K? What does K mean? Equilibrium. Would a battery at equilibrium, what does that mean? It's dead, okay? We need a potential difference going in one direction, okay? So a battery at equilibrium is not going to work. So instead of saying K, we say Q. But the setup is the same. We do the concentration of the products raised to the coefficients divided the concentration of the reactants raised to the coefficients. And what equation am I talking about? Remember I kept saying yesterday, you got to write your overall balanced equation, and I kept having you draw the line here and writing it there, okay? That's where you're going to get your coefficients to raise to the exponent. So let's go ahead and do this problem. All right, there's not a problem on this page. Let's go to the next page. Calculate E naught for the reaction of zinc plus 2 goes to zinc 2 plus copper. I said zinc plus 2, I meant copper. What anyway? I can't read. I'm not on my game today. I don't know what my problem is. I'm probably never on my game on the mic. But so it's telling me E naught. So right now, this is just a regular problem we already know how to do. We need to calculate E naught first. Most of the Nernst equations are broken up in multiple steps like this. They're trying to help you through the problem. So how do I do this? Break into half reactions and look them up. Y'all's favorite thing to do. All right, so this is 0.340 volts. Zinc, did y'all get negative 0.762? Okay, so it's negative 0.762, but because it's oxidation, we're going to flip it and make positive 0.762. And so we get an E naught of 1.3 decimal places, that many volts. But we had better get ourselves a balanced equation here. Luckily, we have the same number of electrons gained and lost, so it pretty much already is balanced. All right, so there's our balanced equation. I know to do that because I know what's coming. I know I'm going to need those coefficients, those ones in that balanced equation. Calculate the E cell when the ratio of these concentrations is small. That is when the zinc plus 2 concentration is 1 E negative 4 and the copper plus 2 is 1. How do I know I use the Nernst? I am not at standard concentration anymore. There's something other than 1 molar. When there's something other than 1 molar, I got to use it. So I'm just going to rewrite it. E of the cell is equal to E naught minus .059 over N times the log of Q. Really quick, I'm going to write what Q is using that balanced equation. Remember, these electrodes are solids. What can you tell me about solids and equilibrium expressions? They don't go. So this Q is technically going to be the zinc plus 2 concentration raised to the first, because there's a 1 in front of the zinc, divided by the copper plus 2 raised to the first, products over reactants. All right, let's plug them in. E of the cell is equal to E naught is 1.102 minus 0.059 divided by 2 times the log. What goes on top? Zinc plus 2. Do I have its concentration? 1 times 10 to the negative 4th over 1.0. Now, before you plug this in your calculator, there's going to be times you might be asked the question, did the cell voltage increase or decrease? And it's in a non-calculator section. And you're going to be like, what? I can't do this problem without a calculator. I can't tell you if the voltage is increasing or decreasing. Yeah, you can because you know your log rules. What is the log of a number less than 1? It's negative. A negative times this positive, a negative times a negative is a positive. So what does that do to the voltage? It makes it higher. It increases the voltage. So you need to know your log rules. If this were a number greater than 1, the log would be positive. So you'd be subtracting off from the original cell voltage, and that would decrease. So we better see an increase in voltage here. So go ahead and plug it in. You're not going to see drastic increases when you do these problems. So don't expect it to go to 27 volts or anything like that. It's a very, very small amount. And everyone do it. Your final E cell should be equal to 1.22 volts. Not a huge change, but this would be a really common thing in industry they use if they wanted to figure out how to produce more voltage in their plating process or something like that. They could say, oh, I'm just going to change the concentration of the zinc, or I'm going to make more copper or something like that. All right, last problem of the day. It's another really long, tiring day of chemistry. I'm telling you, it's cake from here on out, guys. After what you've been through, we got nothing left. All right, until April 1st, and then the fun begins. Calculate E cell of a cell which is made of silver 1 at 0.2 molar, and cadmium 2 at 1.5 molar. Uh-oh. What do I need to do? We're not at standard conditions. I need E cell, so eventually I'm going to have to use the Nernst. Good. Write the half reactions. And how do I write them, though? As what kind? Let's write them as reduction to see which one is reduced and oxidized. What's my goal in doing that, though? To find E naught. Okay, that's what we're looking for first is E naught. So I've got silver 1. Gosh, y'all, the board is going wacky. I did not write it like that. That looked like a Chinese character. Come on. Ag plus 1 electron makes Ag. And then CD2 plus 2 electrons makes CD. All right, so my silver from the table as reduced is 0.799. Cadmium from the table is 0.402 volts. Oh, negative 0.402 volts, excuse me. So which one is more apt to be reduced? Silver. So we're going to leave silver alone, and we're going to flip the cadmium. So we get cadmium going to cadmium plus 2 electrons, and make it positive 0.402. We have got to figure out this voltage because they want E naught, and to 3 decimals, it comes out to be 1.202? 201, really. 1.201 volts. Knowing what's coming, that we have to use the Nernst equation, I've got to get a balanced equation. So to do that, what's going to be my common factor? 2, so I'm going to have to multiply this top one by 2, and I get 2 Ag pluses plus CD gives you 2 Ags plus CD plus 2. Okay, so now let's Nernst this puppy. E is equal to E naught minus 0.059 over N times the log. Let's just write out Q in terms of its symbols. What product do I write? CD plus 2 to the first divided by Ag plus to the second. Okay, let's plug and chug. I want you guys to definitely Spock this, okay? Do your unsubstituted equation first. because this is so easy to make a math error that if you don't show your work and you get the wrong answer, you're up a creek big time. So definitely 1.2. Oh my God. It's possessed. Now it's dead. Is it blinking? Oh my God. That's crazy. Yeah. People at home are going like, what is she doing? I'm actually writing the correct numbers on there, but it's not letting me. Keep working. I'm going to pause the recording until I get this fixed. Okay, so I plugged in all the numbers, and in doing so, we ended up with a final voltage of, what'd y'all get? 1.155, so it's 1.16 then? It's 1.15. It's 1.15. We got the whole rounding business straightened out. Good job, guys. No, it's my lack of understanding of what y'all are saying. Okay, so that's the Nernst equation. Again, you're going to have to practice it. Whenever you see something other than 1 molar, this is what they're trying to get you to do. Okay, any questions? Yes, Julian. But it's not at equilibrium, but if you think about it, it actually kind of can be in equilibrium because you can push the electrons the other direction with a power supply. So you could reverse the reactions. It's just not happening simultaneously. Because if it were, and then mathematically, if K is equal to 1, what's the log of 1? 0. And then, well, then that would mean E is equal to E cell. Whatever, it's not at equilibrium. Okay? But good question.